So in this lecture, we will discuss the one of the main applications of diode. Those are as an rectifier and as an voltage regulator. For rectifier applications, we will use an ordinary diode. For voltage regulator application, we will use Zener diode. And if you see ordinary diode, will have a doping concentration, moderate doping concentration, and whereas Zener diode will be highly doped. So before going to the further discussion, first let us see what is this actually doping concentration means. Okay, let us say for example, I consider the intrinsic semiconductor which is silicon. I want to dope this with the help of trivalent impurities, that is boron, and the doping concentration of the boron is 1 in 10 power 8 per centimeter square. So if anybody know, can you tell me what is the meaning of this 1 in 10 power 8? 1 in 10 power 8. Meaning of this?
Those many number of molecules, sir.
Yeah, I am saying the boron doping concentration to dope silicon is 1 in 10 power 8. So what is the meaning of this? 1 in 10 power 8 means how many boron atoms will be there for how many silicon atoms you are doing. So that information told by this. So anybody have any idea? So the meaning here is 1 boron atom for 10 power 8 silicon atoms. The doping concentration, if I am saying 1 in 10 power 8 per centimeter square, means in per centimeter square area, I am using 1 boron atom for 10 power 8 silicon atoms. In the same way, if I am saying 1 in 10 power 5, same boron atoms. So what is the meaning of this? 1 boron atom for 10 power 5 silicon atoms. So let us say this is 1, this is 2. Tell me which one is the highly doping concentration? More doping? Whether 1 is more doping or 2 is more doping?
2.
Yeah, 2 is the more doping, because see the availability of boron atom for here 10 power 5 silicon atoms only sharing 1 boron atom, whereas here 10 power 8 silicon atom sharing 1 boron. Meaning, simple example, let us say one banana is there. If one banana is there, if it has to share by 10 people, you will get some good amount. If the same banana want to be shared by 20 people, then obviously almost you will get very less only, right? Same here. So here banana is shared by 10 people, means one atom is shared by less people, less silicon atoms. So this is, so more doping concentration means you will get more banana. So 1 in 10 power 5 doping concentration if you use in p-type and n-type material, and with the help of those p-type and n-type material, if the junction is formed, that is Zener diode. Whereas this is moderate doping that is used for ordinary diode. The same way there is lightly doped will be there, so that is around 1 in 10 power 11 or 10 power 12 doping concentration it is. So usually we will see the applications with the help of moderately doped and highly doped diodes. And please note, so this ordinary diode, the situations inside the device will be completely different from this Zener diode inside. How the electric field will be there inside, how the depletion region will be there inside, how the velocity of the electron will be there inside, that is totally different when compared to the Zener diode and ordinary diode. So please note whatever whatever the characteristics you know for ordinary diode, there are bit changes in the Zener diode. So all those things we will see in today's class. So just a brief recap, whatever we need from the previous class discussions is mainly we will use ideal diode equivalent model, whereas when you are solving the problems we will use approximate model. Depends on if he given the diode forward resistance also, we will use piecewise linear model also. Please note, forward resistance means generally they may give dynamic resistance of the diode, or they can directly mention the forward forward resistance of the diode. So here only, if diode will have two types of resistances, that is, one is static resistance and one more is dynamic resistance. So generally static resistance is called as DC resistance of the diode, whereas dynamic resistance is called as a AC resistance of the diode. So one of the main application of ordinary PN junction diode we will see now. So that is rectifiers. So there are three types of rectifiers we will discuss. So please pay attention in coming discussions. We will try to see all the characteristics regarding the half wave rectifier properly. Then same thing, same properties we will replicate to the center tap rectifier and bridge rectifier. So I'll try to concentrate more on the half wave rectifier so that it is easy for you to adapt. Later I'll simply just replicate on whatever we understood from the half wave rectifier. So center tap full wave rectifier and bridge full wave rectifier. So for half wave rectifier, it will use only one diode. So anybody any idea how many diodes were used in center tap full wave rectifier? Do you remember how many diodes were used?
Two, sir.
Two, right? So center tap full wave rectifier will uses two diodes, and bridge full wave rectifier will uses four diodes. So generally, as an electronic engineer, we will always work on DC power supply, right? DC power supply, but DC power supply we won't get directly, right? Either you will get some battery, or you need to convert whatever is available in our home. So the AC supply we need to convert. So in the process of converting AC supply to DC supply, so rectifier plays a major role. So rectifier is a circuit which converts AC to pulsating DC. It's not pure DC, pulsating DC. So if you see the basic block diagram of DC power supply from AC supply, so the AC supply waveform will be like this. Waveform will be like this, sinusoidal waveform with a frequency of 50 Hz. So with the help of step down transformer, we will reduce the amplitude of the signal. So say input obviously 230 volts, 50 Hz it is. So from that we'll try to step down to some less voltage with the help of step down transformer. So that voltage will be given to the input of the rectifier. Means the input of the rectifier is the secondary of the transformer. So the output of the secondary of the transformer will be the input of your diode rectifier. So the input will be, this is your input to your diode rectifier. So among whatever we see in the three rectifiers, the best one, if we consider, the best one rectifier output will get like this. That is full wave rectifier. So in this output, it is not a pure DC, it is pulsating. In this both AC components we're also calling it as ripples, and also DC components it will be there in this output. So this will be given as input to the filter. There are usually basic forms of filters were capacitive filter and inductive filters. So the filter output will be, it will almost smoothens the applied input. So the output available at the filter is shown here, but you see there are some minute ripples are still present in this. So finally, this filter output is applied as a input to the voltage regulator. So at the input of the voltage regulator, there will be some fluctuations in the input, but whereas you see the output of the regulator, the output will be constant. So all these things we will try to see in coming discussions. Well, I'll trying to understand this half wave and full wave rectifier. I'm assuming that wherever diode is there, that diode is ideal diode. So once I properly understood the ideal diode analysis, I can replicate on that practical diode and all the other practical aspects. So when I'm analyzing the circuitry, I'll assume that diode is ideal. So if it is forward bias, I'll replace with short circuit. If it is diode is reverse bias, I'll replace with a open circuit. Fine. First, we'll see the operation of half wave rectifier. So you just see this is the circuit of half wave rectifier and try to understand. I just want to emphasize on the each and every signal and every element of your circuitry. That is only my emphasis. So in between, if you have any doubts, please let me know. So the orange color signal is your input, which is more magnitude, and this black color will be with the output of your secondary transfer at the secondary of the transformer. So this black color signal will be applied as an input to your rectifier. So this is at here is the your input. So that input we are assuming it as Vs. Vs we are then commonly assuming to make the input of all the rectifiers as Vs only. Vs may be varies based on the circuit to circuit. The relationship between Vs, whereas the Vs is input to the rectifier, and whereas V2 is the voltage available at the secondary of the transformer. Some of the cases these two are the same, and some of the cases these were different. So to avoid all the ambiguities, I am assuming that the input appeared at the input of the rectifier is Vs. So for half wave rectifier, so during positive half cycle, plus is connected to the polarities were shown here during positive half cycle, which is in black color. The primary polarities were plus. So positive half cycle means from 0 to pi. So same signal will be available at the secondary with a reduced amplitude, that is black colored waveform that is available here. So the polarities of that signal is shown here in black color. Now the plus is applied to the anode of your diode. So diode D1 becomes forward biased. Once the diode D1 becomes forward biased, the equivalent circuit will be shown here. Once the diode is forward biased, so the equivalent circuit is shown here. Replace with the short circuit, considering the secondary of the transformer. And now I am assuming the ideal diode. So I am neglecting here in the circuitry. I am neglecting the diode forward resistance and also transformer this secondary winding resistance. This windings, some wire is there means it will have some resistance, right? So that resistance also I am assuming it as 0 for simplicity of analysis. So if you see properly, so this is Vs during positive half cycle. Same will be available at the load resistance RL. So during positive half cycle, V naught equal to Vs. So V naught equal to Vs. So V naught equal to Vs, same uh, same will replicate here, because we assume that ideal characteristics is RF is 0 and uh, transformer secondary winding resistance is 0. Now if we see the equations, so Vs, so for mathematics, this is for waveform we got. So for mathematical equations, so we need at least RF, diode forward resistance, because whether diode is present or not, how we'll try to incorporate in equations form. So for equation purpose, we will use forward resistance. We will use forward resistance of the diode, whereas we will still neglect the uh, transformer secondary winding resistance. So in this, if you apply KVL in this, considering the second sign, I will write considering the second sign. So Vs minus Rf I naught minus considering second sign minus RL I naught equal to 0. So from this I naught you will get Vs by Rf plus RL. So you just remember this, during positive half cycle, the I naught equation is, I naught means this is I naught is comprising both, because this is current in this loop, right? In this loop, right? Current in this loop. So we cannot say that whether it is AC current or DC current. It is comprised both, right? Because the input is sinusoidal in nature. So the input is sinusoidal in nature. So, and from this equation, the input is I naught equal to Vs by Rf plus RL. It will be reduced, the I naught magnitude reduced by a factor of 1 by Rf plus RL. That's why here I naught magnitude, this one, I naught magnitude is reduced compared to the V naught. Okay. So these are the equations and waveforms during positive half cycle for half wave rectifier. In the same way, during negative half cycle, the polarities at the secondary of the transformer will be inverted like this, minus and plus. As minus is available at the anode of the diode becomes reverse biased, replaced with the short circuit. So if you see the waveform, because the output is not connected to the secondary of the transformer, so the output simply becomes 0. Simply becomes 0. So during negative half cycle, output voltage is 0. As voltage is 0, current is also 0. So putting these two informations in the waveform, so during positive half cycle, diode will be on, and the output voltage waveforms and current waveforms will be shown here. So this is positive half cycle. From pi to 2 pi, that is negative half cycle, the diode will be off and the output will be 0. So same continues during again next consecutive cycles. So this is the waveform. Now we will see the equations. So we already seen from the during positive half cycle operation, I naught equal to Vs by Rf plus RL. That is during positive half cycle. During negative half cycle, I naught equal to 0. Fine. But to analyze the output of the half wave rectifier, we need to use the mathematical quantities. How those quantities were mean value or average value, mean square value, root mean square value. Let us say, please try to observe if the waveform is like this. Okay, can you, and means for a sinusoidal waveform, please tell me what is the mean value for a sinusoidal waveform?
0, no, sir.
Yes, 0, right? So can you tell me the formula for mean value? Let us say this is x of t. If this is x of t, what is the formula for that? Mean value or average value. Mathematical formula I'm asking, if anybody remembers. That is, if I consider till here is a t, is t from here to here. One cycle time period is t, then the average value of that waveform will be 1 by t integral 0 to t x of t dt, right? Mean value. Mean value, this is the formula, right? For a one cycle, you need to integrate, then you will get mean value. So if you do the sinusoidal, if you find the mean value for the sinusoidal waveform, substituting in this equation, you will get 0. Right? Same way, if it is mean square, simply this is x square will come. Same formula, x square of t. Right? Same. All same only will come, mean square. The same way, root mean square value. Root mean square, that is RMS only, right? Root mean square. Same mean square, that entire formula will come, right? Right? Root mean square value. These are the usual mathematical definitions. So we will use these definitions to analyze my output waveform. How much generally mean value or average value gives the DC value present in the waveform. DC value. That only, right? How much is DC is present in my waveform. So for same sinusoidal, tell me RMS value for this sinusoidal. Let us say this is peak value is Vm. If the peak value of the sinusoidal is Vm, please tell me what is the mean square or root mean square value? If you remember. For
0.707 Vm.
Yeah, that 0.707 is Vm by
Root 2.
root 2. So by the end of this lecture, I want at any point what is the average value and RMS value. These two always try to understand from each and every point. Okay, you understood, right? For basic sinusoidal waveform, mean value is 0, mean square value is root mean square value is Vm by root 2. Fine. Now I will find for this I naught mean value. I will find. I know the mathematical definition. So this mathematical definition simply I will substitute in the equation. So this was the mathematical definition. So Vs by Rf plus RL, where Vs equal to Vm sin omega t, where Vs equal to Vm sin omega t. So Vs will have a peak value of Vm. So that's why that peak value, if you substitute, you will get here see Im sin omega t. How you will get this is simply I'll substitute in this. Peak value of Vs is Vm by Rf plus RL. As you know, we already I naught equal to, this is I naught equal to Vs, right? So I naught maximum value want to get, you need to substitute the peak value of Vs. So that is Vm by Rf plus RL you will get. Okay. So this quantity only is assumed as Im. Vm by Rf plus RL quantity is assumed as Im. So Vs means Vm sin omega will come, right? I naught. So I'm saying I naught is the previous quantity. So from that, taking the peak values. So I naught equal to, obviously you will get I naught equal to, you will get Im sin omega t. So the relationship between peak voltage and peak current is this. Im equal to Vm by RL plus Rf. Fine. Now I naught is this only, right? This waveform only, right? So in this waveform, if I find out average value, so simply what one complete cycle is from 0 to 2 pi, right? That only here it is doing 1 by 2 pi integral 0 to 2 pi I naught d omega t. So I naught will have different definitions. That's why we're splitting the integral. So from here you see I am sin omega t d omega t. We bring out I am sin omega t integration is minus cos omega t. So as it is the definite integral, you will substitute the upper limit and lower limit. So minus cos pi minus of minus cos 0. Minus cos pi value is plus 1, right? Minus cos pi is cos 180 plus 0. So minus cos 0 is minus 1, minus of minus plus 1. Same way, minus cos 0 is minus 1, here minus is there plus. So finally we find out the average value for the output of the half wave rectifier. This is the output of the half wave rectifier, right? This is the output of the half wave rectifier. For this, if you found out average value, you will get, that is Im by pi. So that average value only IDC. Fine. Same way you can do for voltage waveform also, same integration, doing integration, but in the circuitry there is a Ohm's law relation is there, right? So the same Ohm's law relation we will try to use. So this is the circuitry, you see, this is a circuitry. In this circuitry you want at load this VDC is the V0 DC actually. At load you need output DC value. So obviously output will be appeared across this RL only, right? Output will be appeared across this RL only. So that's why VDC equal to IDC into RL. Okay. Previously we seen I0 comprises both AC and DC quantity. Now in that I0 is a combination of IDC plus IAC. It is having both, right? Both components are there. Fine. Those components, if you want to see, you just see here the IDC in this waveform I shown in like these lines. So if you find out Im by pi will be always less than Im. So this is the DC value present in the output waveform. So Im by pi, if you locate in the output, at here you will get Im by pi. So as we are finding the output voltage, we will only use output DC voltage. We will only use output DC current. So from that, as the DC voltage will be available at only load, that's why the equation VDC equal to IDC into RL. So IDC you already found out. You will substitute IDC value, that is Im by pi, but Im, you know, Im equal to Vm by Rf plus RL. So if you substitute in this, VDC equal to Vm by Rf plus RL, and if you try to bring it all the quantities one side, so VDC equal to Vm by pi RL Rf plus RL. This is the actual equation based on the analysis. But to make our mathematical analysis even easier, we will assume that generally the forward diode resistance is in the range of ohms. The load will be in the range of kilo ohms. Assuming that means forward resistance of the diode will be much lesser than the load resistance. So this quantity Rf plus RL will be RL only. So RL will cancel each other, so that VDC equal to Vm by pi. Fine. Now till now we found out output DC voltage, output DC current we found out with the help of average value definition or mean value definition. Same way we want to find out AC quantities. we will use the definition of RMS value. RMS value, the basic definition anyhow you know, square of area under the one cycle of the output current by time period of the output current. So that only. So I told you the basic definition. So following the basic definition of RMS value, so I want to find out RMS value for I naught. So IRM is equal to square root of integral to 0 to 2 pi I naught square d omega t by 2 pi. So 1 by 2 pi I will make it common, and then I guess we can solve this. So I'm going for the final results. Sin square omega t is there. If you can write that 1 minus cos 2 omega t, and if you and if you solve, you keep on solving, finally you will get Im by 2. Please note, and this is very, very important. People are confusing the RMS value of this waveform is Im by 2. Okay. So the RMS value of this waveform is Im by root 2. So this waveform is Im by 2. And same, so at the output, you are finding the voltage. That's why Vrms equal to Irms into RL. So you will substitute the IRMS value, and if you keep on solving, Im equal to Pm by Rf plus RL. Please try to remember the formulas. Vrms equal to Vm by 2 multiplied by RL by Rf plus RL. So Vrms equal to, you will get, and neglecting Rf, you will get Vrms equal to Vm by 2. So for half wave rectifier, IRMS equal to Im by 2, Vrms equal to Vm by 2. Okay. So in the output, some quantities we found out with the help of mathematical definitions. So, but the nature of the output, if you want to tell, you need to take the rectifier parameters. Those are ripple factor, rectifier efficiency, and peak inverse voltage. These three quantities were very important in deciding the how good the rectifier is. Ripple factor is the ratio of RMS value of AC components present in the rectified output to the DC components at the rectified output. Means what this ripple factor will talks about how many ripples were there, at the output of the rectifier. Okay. So whether you want more AC ripples at the output of the rectifier or lesser AC ripples, how many you want, more or less? Can you please respond? In the rectifier output, whether you want more AC components or less AC components?
Less AC component.
Less AC components, right? If less AC components means this quantity will be lesser. If this quantity will be lesser, the ripple factor gamma has to be lesser, right? Lesser, right? Means for a good rectifier, the AC components has to be as less as possible in the output, so that the ripple factor has to be as less as possible. If ripple factor is more, means the output is not good. The rectifier output is not good. The preferred value for ripple factor is as less as possible. But to find out AC components RMS value, you don't have separate waveform is not there, right? The output is available with the combination of both AC and DC. So to find out the ripple factor, we will use the relation, mathematical relation. The total RMS value in the rectified output is whole square equal to DC value square plus RMS value of AC component square. So from this relation, you keep on solving, then you will get a ripple factor gamma equal to Vrms by Vdc whole square minus. In this, if you substitute, we already know Vrms value of the rectifier output, Vdc value of the rectifier, half-wave rectifier output. If you substitute in this, you will get 1.21 ripple factor for half wave. Okay. The same way, rectifier efficiency is a ratio of power output out DC output power at the output of the rectifier by AC input power. Means how much AC is converted to DC. Let us say if you given 100 volts AC, you should try to expect 100 volts DC is coming, means the conversion efficiency is 100%. Without loss of any energy, you try to get. But that is ideal, right? You won't get because of the practicality conditions. So ideally, we will expect if you apply some 100 watts of AC power, we'll try to get 100 watts of DC power. Means if you get 100%, this efficiency is 100%, means that rectifier is very, very good, right? So the rectifier efficiency has to be as high as possible or as low as possible. The rectifier efficiency has to be as high as possible. So output DC power, how you will find out? Output DC power, because this is output only, right? If output is there, means only load will be there. Only load will be there. That's why, because it is the DC power, we are considering only the DC current. IDC square into RL. IDC square into RL. So for half a rectifier, we will substitute the IDC value and we will find out P naught is equal to Im square RL by pi square. Same way, PIAC, IRMS square into RF plus RL. See, because here we considered both diode resistance and RL resistance, because you need the power at the here. This is PIAC, right? The power at the input means this is only, right, the secondary of your transformer. So PIAC. So when you want power here, the voltage at here and the RMS current, you will consider RMS current in this loop. So then it will give you the power at here. So when you are finding the RMS current, the current is flowing through both RF and RL. That's why you will consider both resistances there. That's why we will consider for input AC power, we will consider both resistances, IRMS square into RF plus RL. So if you substitute finally, and if you approximation, if you do RF is much lesser than RL, you will get efficiency 40.5%. Means if you give 100 watts input power, you got 40.5 watts DC power. Almost 60 watts of power is wasting in the form of losses for half wave rectifier. And very, very important parameter for an rectifier, that is peak inverse voltage. You see the definition is the maximum reverse voltage that can be applied to a PN junction diode without causing any damage. So this can be realized like this. So whenever diode is there in the circuitry, let us take the circuitry half-wave rectifier circuit only. See, whenever you are applying during reverse bias. So as you know, ordinary diode has to be operated within the reverse breakdown region only, right? should consider this is reverse breakdown voltage. When you are operating the ordinary diode in reverse bias, you need to apply below this only. But and I think you already experienced in our labs also. See, whatever the diodes IN 4001 and BY 127 we used in the labs, those having the reverse breakdown voltage 50 volts, and the maximum power supply which is available in our labs is 30 volts, right? So even though you are completely applying the 30 volts, the diode won't damage. So that safety we already considered. Means this peak inverse voltage talks about in a circuitry how much is the reverse breakdown voltage is appearing across the diode. So if I apply here Vm, if I measure the voltage here, the maximum voltage will be appeared here is Vm only, right? Because this is Vm, and the voltage drop across this RL is 0 because current is 0. So the same Vm will be appeared here. So the maximum voltage in this half-wave rectifier, maximum reverse voltage appeared across this diode is Vm. So the peak inverse voltage for the diode used in half-wave rectifier is Vm. So when you are how this peak inverse voltage is useful for designer. So the designer will select such a way that, let us say, peak inverse voltage is Vm for half-wave rectifier. Let us say Vm is 30 volts. So you know that as a designer, you know what is the maximum voltage you will apply to your circuitry, right? So let us say if Vm is 30 volts, you will select the diode will have a reverse breakdown voltage slightly more than 30 volts. Let us say 35 volts, reverse breakdown voltage 35 volts or 40 volts. But for safety, it will be selected double the peak inverse voltage. If 30 volts is there, the diode selected to operate in the half-wave rectifier circuitry or in the rectifier circuitry is double the peak inverse voltage, which is 60 volts. The diode which is having reverse breakdown voltage is 60 volts. Means if you try, if the applied voltage is crossing 60 volts, the diode will damage, diode will burn directly. So for that safety, based on the circuit operating voltages, if the circuit operating voltage is 30 volts, we'll try to select the diode which is having the reverse breakdown voltage 60 volts. So like that, the peak inverse voltage is responsible in selecting the diode. Any doubts still here? Okay, how it is Vm is shown here. Same, you will apply KVL, second sign, and if you found out, you will get the voltage across here is equal to the voltage across here. Fine. So shall we revise the whatever the formulas we know till now? First, we'll go with IDC. What is IDC? What is the formula for IDC? IDC for half-wave rectifier is, yeah,
Im by pi.
yeah, Im by pi. VDC equal to, we don't want approximated formula, I want exact formula. VDC equal to Vm by pi multiplied by RL by RL plus RF. So it is not coming properly. So VDC equal to Vm by pi multiplied by RL by RL plus RF. In the same way, IRMS is Im by pi, VRMS Vm by pi multiplied by RL by RF plus RL. And what is the ripple factor for half wave rectifier? How much is the value you got? What is the definition? Ripple factor.
Sir, IAC by IDC.
Yeah.
Sir, IAC by IDC 1.21.
Yeah, IAC by IDC. So, but to use for mathematical formula, we will use square root of either VRMS or IRMS by IDC whole square, right? Minus 1. And what is the value? What is the value? 1.21, right? So this one, ripple factor, this formula I'm asking. And efficiency, output DC power by input AC power multiplied by 100. So means it will select the how much efficiency, how much efficiently the rectifier converted the AC to DC. So ripple factor has to be as high as possible or as small as possible. Ripple factor. Yeah.
Low as possible.
It should be as low as possible, and rectifier efficiency should be as high as possible. And peak inverse voltage is decides the maximum reverse bias voltage of the diode, which decides the selection of the diode. The diode, how much it should have the reverse breakdown voltage, that will be decided by peak inverse voltage. Fine. So, but the problem in the half wave rectifier is it is only one diode. It is conversion efficiency is very less. More AC components is present at the output. Almost half cycle is conversion is not happening, right? In a half wave rectifier. To avoid all those disadvantages, we are going for the full wave rectifier. The full wave rectifier, there are two types are there. One is center tapped, and one more is full wave bridge rectifier. In center tapped, we will use two diodes like this, and the secondary of the transformer is having 3 terminals. One ground like this. So during positive half cycle, what will happen? And before understanding the operation of the circuitry, please see the network concept. If the current is entering at plus here, if I measure the output voltage here, current is entering there, and this is V1. So there I will get V, as you seen in the basics, wherever current is entering, there I will put plus sign. Wherever current is leaving, there I will put minus. So when the current is entering, plus, current is leaving, minus. So in this case, V0 equal to V1. So if the reverse the current direction is at here, entering from bottom and leaving from top. So if you measure the voltage across there, obviously V0 equal to minus of voltage drop across that resistor, right? This will be fine. So same concept, only I will use when I am deciding the output, whether it is positive or negative. Okay, see, during positive half cycle, the equivalent circuit will be, means the polarities of secondary center tap transformer is like this. During positive half cycle, primary plus minus like this, but this is secondary plus minus plus minus. So plus is applied to the diode D1, minus will be applied to the diode D2. So diode D1 will be forward bias, so replace with the short circuit. Diode D2 will be open circuit. So now if you see, so here this the center tap is one more terminal is grounded, So this will be realized like this also, right? Right? So for simplicity, for easy visibility, I removed this. So one ground here means there will be a connection is there here. So now if you see the current direction, starting from the plus of the secondary transformer, current will flow like this, like this, like this, like this, and current will again reach the negative of the secondary. So means complete loop, right? Current will flow. So if you see whatever Vs is there here, same will be available here. But please note here Vs equal to V2 by 2, because V2 is the net voltage, effective voltage, I can say effective voltage of the secondary of the transformer, that is divided as Vs and Vs. The relationship between this is, as this V2 is divided as two quantities, so Vs equal to V2 by 2. V2 by 2 means half the voltage will be available. So same, that is only the thing to be remembered, but shape anyhow it won't change, right? Whatever is available at here, same will be available at the load. So same during positive half cycle. During negative half cycle, minus here, minus plus. D2 will be forward bias. Now the current direction will be from bottom to up and again reaching here. And please note in the both the cases, the current is entered at here only. Current is entered at here only. So both the magnitudes and phase were same only. Magnitudes and phase will be same only. Like that only I am concluding that how you will get if you apply input like this, but the output you will get like this, or following the network analysis concept, as the in the both the cases the current is entering at the same point. That's why I will get at the output this shape. So if you seeing the final output of center tap full wave rectifier will look like this. So now if you see the derivations, that is VDC, IDC, VRMS and IRMS. Now whether I need to find out, this is the output of full wave rectifier, whether I need to find out for 2 pi duration or pi duration. If I want to find out that, you know the basic definitions, right? Basic definitions only will follow for one complete time period. So the time period of this waveform, full wave rectifier output, what is the time period? Yeah, what is the time period?
So pi.
The time period of this waveform is pi. So in the derivations we will use always pi only. So it is clearly mentioned here, you see. So the derivations, all the derivations when I am doing, I will follow only for pi duration. Anyhow, these things you already seen how it will come. You will once again check it out. So if I want to find out for a full wave center tapped full wave rectifier output IDC, instead of 2 pi, I will find out for pi, only because the output of the center tapped full wave rectifier is having the time period pi only. So one cycle, if you do the integration, that will give you the average value. So if you same substitute, you will get IDC equal to 2 Im by same procedure what you did if you previously do, you will get VDC equal to 2 Vm by pi after approximation. So approximation formula is same, that RL by RF plus RL won't change. Same RMS value for 0 to pi only. If you find out, you keep on solving the integration. One second, it is scrolling. So IRMS equal to Im by root 2. Please note this IRMS is for this waveform. you may have a coincidence for this waveform also, sinusoidal waveform also, you will get by root 2, but you try to differentiate both. For this waveform, if I applied mathematical definition, I am get Im by root 2. For that, it is just a coincidence. For the sinusoidal waveform also, I will got same result. It's just a coincidence. So please don't confuse between these two. So RMS load voltage obviously is Vm by root 2. So that is for this waveform. Means this is current waveform, same voltage waveform, same the current wave shape and voltage wave shape is almost same, right, with some magnitude changes. So for that waveform, if you find out RMS value, that is Vm by root 2. So you substitute in that ripple factor, you will get 0.483, and rectifier efficiency you will get 81.2%. And please observe this peak inverse voltage. So peak inverse voltage, if you see the Vs, and see during positive half cycle, you will find out the peak inverse voltage at reverse bias diode, right? That is at D2. You will always find out peak inverse voltage at reverse bias diode. So during positive half cycle, this is the equivalent circuit. So peak inverse voltage you will find out. So this is anode and cathode. So peak inverse voltage you will find out at cathode plus at anode plus. So if you find out here with the help of this equation, you will get peak inverse voltage equal to 2 Vm. Meaning, if you are applying in 30 volts signal, the peak inverse voltage will be almost doubled. So for safety reasons, if you selecting the diode, double that of it. So if peak inverse voltage is 60, you need to choose for safety reasons the diode which is having the reverse breakdown voltage 120 volts. It is huge, right? Your operating is 30 volts, but you need to select the diode which is having the breakdown voltage 120 volts. Whereas in half wave rectifier case, you have to select the diode which is having the reverse breakdown voltage 60 volts or more than enough. So the only disadvantage in the center tapped full wave rectifier is, one is the center tapped rectifier is very bulky, and also the two diodes only there. Always more work on these two diodes. If any one diode damages, you won't get the output only. So the circuit maintenance is more, and also the circuit will have more peak inverse voltage. So to avoid these disadvantages, we are going for the bridge rectifier. We are going for the bridge rectifier. So please try to understand the bridge here, starting from, let us say, 1, 2, 3, 4. So the direction is always goes like this, and direction continues and will end at here. So at here you will apply input at these two terminals. You will select the output, that is 1 and 3. This is 1 and 3. At 1 and 3 you will take the output. So diode direction is simply outward, and again we'll try to combine this one. We'll try to combine, and at here you are taking the output wherever the diodes are combining. So you remember like that, so that it is easy for the remembering the diode directions. Once the diode direction is proper, the circuit analysis is very easy. Same. Now during positive half cycle, here plus is there. So diode here plus means here plus, here minus. So diode D2 will be forward biased and diode D1 will be forward biased. These two diodes here there, those are reverse biased. So once it is forward biased, the current direction is always will enter at the load here. Reaching like this. Fine, closed loop. Same way during negative half cycle. So this is minus here, this is plus here. So these two diode plus is connected to anode of D2, so it will be forward bias. D4 cathode is connected to minus, so D4 will be forward bias. So now the current direction always start from plus. Again, at same point only the current is entered, so both the magnitudes were same. Magnitude and directions were same. Closed path again like this. So the output will be shown like this. So this is the current through diode D1 and D2. This is current through during negative half cycle. This is during positive half cycle. Fine. So this is the overall current. If the current is like that, voltage also almost following the current wave shape only, right? So only thing is now the disadvantage of the center tap rectifier is overcome by the bridge rectifier. That is how it is rectifying. The peak inverse voltage, whatever is you are measuring, will be divided among the forward bias diodes, so that the peak inverse voltage for a bridge rectifier you will get Vm. And when you are doing the derivation, this is Vm by Rf plus RL for center tap full wave rectifier, whereas for bridge rectifier, two resistors will be there, right, in the path always. So this becomes 2R. That is only the change in the entire derivation or in the entire formula. And this is second modification. One second. So same IM, if I consider the secondary winding resistance, in that path only it will be there, right? In that path only it will be there. So this is transformer secondary winding resistance. The IM will changes like this. So once IM is changes, rest of entire derivation will changes, right? Incorporating it wherever, if you find RL by RF plus RL, there you will substitute this below bottom quantity. Wherever RL plus RF is there you will substitute this quantity, because this quantity is usually changing. This is considering the second transformer secondary winding resistance. Fine. Now we will solve some of the problems. We summarize. So these are all the definition, all the calculated parameters of the rectifiers. So please just have a look. We will solve now the problems on rectifiers. So please take down this data. The RF is 10 ohm. is used to supply a power to 1 kilo ohm load resistance from 110 volts RMS source. What is the meaning of this? The secondary voltage, RMS voltage, this is 110. Can you find out the parameters? VAC, VDC, IRMS, IDC. Let's find out these parameters. So first 4 parameters you find out. Peak load voltage is VM. Peak load voltage is VM. So can you tell me how you will find out VM? It is given V2 RMS is given. V2 RMS, which is equal to Vs, is 110 volts. You want VM, you want VM, you want. How you will find out? Yeah, anybody found out VM? How much you got? To find out VM, you has to know the wave shape of this, right? Vs wave shape. Vs will be obviously the input to the rectifier, which is sinusoidal. So the sinusoidal waveforms RMS value, sinusoidal waveform RMS value, where VM is this. Peak value of that is this. Anybody found out? So
77.7 volts.
no error. You will get more. So just see. The Vs wave shape, this wave shape RMS value is given, that is 110 volts, that is RMS. That is RMS is given, right?
155.
Yeah.
155.
Yeah. 155.56.
Yes, sir.
That is Vm by root 2. From this, Vs RMS equal to Vm by root 2. From this we can find out Vm, right? Vm equal to root 2 times Vs RMS. We substitute root 2 times 110 volts. You will get 155.56 volts. Okay. Once you got Vm, it is very easy, right? Same also you can find out peak current Im. How much you got Im? Im equal to Vm by, what is the formula? Vm
RF
by,
plus RL.
yeah, Rf plus RL. You substitute in this formula, you need to get Im equal to, can you do quickly with me? 0.154 amps. Substitute the value. Now IDC IDC equal to IM by pi, right? IM by pi. If you substitute in this, IM by pi, you will get 0.049 amps or 49 milliamps. VDC, find out with the exact definition, then later automatically approximate definition will be remembered. Try to do with exact, so that if the values were given, based on that we can substitute. These days the fractions also, the variation in the fractions were there, means exact analysis only you need to do. So Vm by pi, if you substitute, that is approximate analysis. So Vm by pi multiplied by RL by RF plus RL. How much VDC you get?
49.026.
Yeah, 49.02. Next is IRMS, VRMS. Waiting for your response.
Zero 0.077 amps.
Yeah, 0.077. Same, use exact analysis. Don't use approximate analysis for VRMS. And tell me VRMS. Try to know the units. And these days, rather than objective type questions, the numerical answer type questions were given more weightage. So if you try to answer the numerical answer type, means fill in the blanks type questions, you need to know the exact answer. If you know the exact answer, then only you will get the good marks. And one more advantage there here, even though you know some information about that question, you can try guess and answer it. Even though it is wrong, you won't have any negative marking. One advantage is there, one disadvantage is there during numerical answer type questions. If you know exactly the concept, then only you can able to answer the numerical answer type questions. Please note, numerical answer type questions won't have negative marking. So whatever the concepts you know, try to know clearly. They will definitely touch the concept oriented questions only. So you need to practice more and more. Use this time for best usage. Try to practice more so that you'll get a good rank. If you get a good rank, there are plenty opportunities were there. Now the stipend for MTech is also increased. So it is a good. You will get almost 20,000. And there is a Vishwesvaraya scholarship is there. If your luck is good, if you are there in the NIT, IIT, and if your luck is good, if you select for Vishwesvaraya scholarship, you will get 25,000 per month. This is as per 2 years back data. Now they may increase. So you just think about it once. Almost equal to the software companies or any job salary you are getting as a stipend if you do the MTech. Believe me, if you do masters in any IIT or NIT, definitely your career is in different level only. The placements, especially core companies, placements were very good in NITs and IITs. So if your dream is to go to core companies, either it is government companies or private companies like VLSI companies, it is a good opportunity. Ultimately, you need to get the good rank in GATE. So rest, leave it to the time. Automatically, time will give you back the good career. So these 3 months, try to give your utmost time in solving more and more questions. Make a plan, have a strategy to get a good rank. Aim for score 65 to 70 marks so that you are there in the band of 45 to 50. Definitely you will be there in below 5000 rank. If you are 5000 rank, damn sure you will select in any of the PSU. You are good college admission you will get. Shall I move on? I think you found out efficiency, ripple factor, and peak inverse voltage also. Efficiency, you will get almost 40 point some 40.5% something near to that. Ripple factor 1.231. Moving on to the next problem. Just I am focusing on only how you'll find out VM. Rest of the things, I guess you can able to find out. A 2 diode having means obviously it is center tapped full wave rectifier 10 ohm. If the secondary voltage of center tapped transformer is 230 volts, means V2 is 230. But what you want? It is Vs. Vs equal to 230 by 2, right? 230 by 2. How much you will get? 230, 115 volts. Is not mentioned here RMS, but the secondary voltage it is told means it is clearly AC only. So this is 215 volts RMS. So Vm equal to 2 to 2 times 115. So you will get 162.63 volts. I think for rest of the things you can find out. If you want, you just note down the answers. Later you solve. Peak load current is 0.161 amps. Load current is 0.1025 amps. DC load voltage is 1 or 2.5 volts. IRMS is 0.114, IRMS is 0.114 amps, VRMS is 113.85 volts, peak inverse voltage is 2 Vm, that is 2 multiplied by 162.635, peak inverse voltage is 325.27 volts. Efficiency 80%, ripple factor 0.483. And see, secondary voltage of transformer is 120 volts, deriving full wave rectifier. From this, you can clearly understand Vm is directly given, right? Vm is directly given, right? So this is only Vm. Once you know that, simply substitute the formula and get the values. So for this percentage efficiency, same almost as we find out in the derivations, same only get 80.14%, 80.14%, ripple factor 40.483, peak inverse voltage is Vm, right? Obviously 120. So we'll try to solve the questions. So can you tell me the answer for this? You know some formulas regarding all the rectifiers. Tell me the answer. So make use of this class times so that you don't need to again study by your own. I know you already know these concepts, but I'm just revising. I'm trying to just give you the concepts. It's not, as you know, it is not possible to cover entire analog electronics syllabus in 4 classes only. So how much is possible? How much clarity I can able to give regarding the topics? I can give. Later you can study by your own.
Option B, sir.
Obviously, option B only, right? DC. Using two diodes means center tapped, obviously. Center tap, peak inverse voltage 2 Vm, 2 Vm. VDC is, this is not. Obviously, this. Now tell me. I told you some direction, something in when you are discussing the full wave rectifier, bridge rectifier. Which option is the circuitry for bridge rectifier? It is not mentioned in the question anyhow, but you clearly understand this is bridge rectifier only. Which option? I told some diode directions will start from somewhere and will try to end. There only will take the output. Something I told, something, right? That only you try to remember. Where the directions are starting and where it is ending, there we are taking the output. Something like that.
C, sir.
Yeah, see, diode directions were starting like this, again closing like this. Wherever it is closing, there we are taking the output, right? See, little bit trick to differentiate your concepts till now what you know. So you see here, Vt is the thermal equivalent of voltage or temperature equivalent of voltage. Vt at room temperature, it is usually given in the textbook 26 millivolts, but here it is given 25 millivolts. So we will use that value only. and one more is RD. That is the dynamic resistance of the diode is thermal voltage, right? Thermal equivalent of voltage is by diode current ID. So VT is 25 millivolts is given. So 25 millivolts multiplied by diode current ID. This is the formula we seen from the previous classes. With the help of this, I'll try to solve this. A small signal input, Vp equal to cos omega t, where Vp equal to 100 millivolts. What we need to find out here? The bias current IDC through the diodes. Here you see there are AC source and DC sources were there. You need to find out, because of two sources are there, obviously DC current and AC current will be there in the circuitry. It is here asking only IDC. So when you are doing the DC analysis, as you know, you don't need any AC sources. If AC voltage source is there, simply short circuit it. Now, as it is 12.7 volts and is clearly given, diode will have a forward bias, that is cut-in voltage 0.7. All the diodes are connected in same direction, so all the diodes will be forward biased. So the equivalent circuit becomes like this. Now we need to find out IDC. I think you can able to find out very easily.
1.28 milli, sir.
1 point, huh?
Option B.
Yeah, I guess so. 1.27. I think the answer is 1 milliampere. You see, 12.7 minus, if you add all 0.7s here, all 0.7s here, 0.7s will by 4 will give you 2.8, right? So the voltage here is 2.8. The voltage here is 12.7 divided by 9,900 ohms. You will get 1 milliampere. 12.7 minus 2.8 divided by 990. That only, right? The current here, this voltage you know, this voltage you know, because this is short circuit, right? It's 12.7. Simple circuit analysis concept, right? 1 milliampere you will get. Understood? Can I move on to the next problem? Any doubt? Moving on. The same problem only, if it is asked to find out AC output voltage. Previously IDC is asked, now AC output voltage it is asking. So if you want to find out AC output voltage, you need to replace each diode with the AC resistance, that is RD. So when you are doing AC analysis, you will have only AC. So how much is the dynamic resistance RD of each dynamic resistance of each diode? 25 milliamps. divided by ID. ID you got 1 milliampere. RD you will get 25 ohm. So 25 ohm of 4 resistors were there, right? Obviously, this is 100 ohm. This is 990 ohm. VI. You want VAC. You will use voltage division rule, right? VAC equal to VI multiplied by 100 divided by 990 plus 100, total resistance, right? Voltage division rule. If two resistors were like this is VI, you want V0 here. So 990 plus 100, you will get 10,000. VI multiplied by 1 divided by 100. Whereas VI will have peak value 100 millivolts, right? Means 100 milli cos omega t. That is VI divided by 100. So it is asking VAC. You will get 1 cos omega t milli, right? 1 cos omega t millivolts. I guess if you understand the concepts properly, you can able to answer this. The input is applied here during positive half cycle. The polarities will be like this. What happens to the all the diodes? The input is applied across YZ, means here. Here input is applied, AC input. What happens during positive half cycle? And try to understand the equivalent circuit and get the output. Please try to analyze the circuitry. I'll give 1 minute. I'll after that discuss. I'm audible, right?
Yes, sir.
So at least you got for positive half cycle. Positive half cycle. You see, plus is here. Plus is
Reverse
available
bias.
at. This is reverse bias. Yeah, tell me this one. What about this
Reverse.
diode? Yeah,
Reverse bias.
obviously. This diode,
Reverse bias.
this diode.
Reverse bias.
So will there any possible way to reach W and X? This input applied input. Because across W and X only the load is there. Some resistance is there, right? Across W and X only some resistance is there. If applied input somehow will reach here, you will get some output. But this is open, this is open, this is open, this is open. All are open only. So will you get any output during first half cycle? No, right? Across W and X. So across W and X, output will be 0. Fine. So now during negative half cycle, this is minus and plus. So this is plus, 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 minus, minus. Now we'll draw the equivalent circuitry. Here your source is there. Because all our until unless you won't get the equivalent circuitry, you won't get the ideas. Don't formulate the circuitry in your brain. Try to put it on the paper, see the equivalent circuit, and try to get the output. So here W ohm, here X, here across here. If you expand this W, 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 W here, and if you expand X also, both are shorting, right? Across short circuit, you get any voltage. See, this is W, both are shorting, right? Across short circuit, you get any means here short circuit and resistor are there in parallel. Obviously, short circuit you will get, right? You see here, W and almost are reaching, right? Shorting. Here also short. Means these 2 points are connected only. There you are measuring the voltage. Across a short you are measuring, obviously 0 will get. Again in this case also 0. So which is the answer? D is the answer. 0 for all t. This is the concept based question. Don't confuse. Just the diode D1 is the ordinary diode. That is, it will have P and N semiconductor materials. Whereas Schottky diode, one material will be metal and other will be semiconductor. Metal junctions those are. Schottky diode is a metal junction, and obviously almost near to the diode operation only. When it is forward biased, replaced with the cut-in voltage, that is 0.3. And here, try to always careful. Till now, if plus is there connected to anode, we are assuming that is forward bias and doing it. Finally, we are getting the proper answer only. But whenever very less resistance were there in the circuit, very careful about it. Very careful about it. Because across the parallel branches, same voltage will be there. So let us say, based on this, the nodes applied, both diode D1 and D2 are forward biased, replaced with the cut-in voltage. Let us assume. But this is 0.3 and this resistance is very, very less. And it need to have here 0.7. There may be more possibility that you won't get here 0.7. So that's why I am assuming. So till now, whatever you did based on your till now, however you solve the other problems, like that you try to see. But there is here, if some 200 is there, also fine. But it is 20 ohm resistance. There is ambiguity that more possibility that you won't get rest of the 0.4 here, and so that it will be 0.7, 0.7. It is very less possibility is there. That's why I'm assuming is just an assumption. D1 is forward biased, but not in conduction, not conduct, not conduct. Means that to avoid all this, simply saying it is not conducting. It is not D1 is not conducting. D2 is forward biased. So according equivalent circuit will be, if you get final network equations properly, then whatever your assumption is correct. This assumption will be correct. If you won't get the proper equations are not tallying, then your assumption is wrong. This is forward bias. This is not conducting, means obviously it is not representing the voltage, open circuit. So can you find out current in this? This is 1K, this is 20, this is 10, this is 0.3. Can you find out current with this? Current I equal to 10 minus 0.3 divided by 1020 ohm, right? Find out current, and our finding current I, find out voltage at 20 ohm, voltage across the 20 ohm. Tell me the answer. I will also do with you.
Current is 9.5 milliamps.
Yeah, this is 9.5. Sorry, this one, right? 9.5 and P20 ohm voltage. P20 ohm 9.5 kV multiplied by 2, right?
0.19.
Yeah, 0.19 means here that is 0.19 and this is 0.3. If you see total voltage 0.19 plus 0.3, you will get the voltage across here. This voltage is 0.49, which is less than the cut-in voltage, right? It is less than the cut-in voltage means whatever your assumption that is correct only. That is correct only. So these are the options. So now tell me which one is the answer.
D, sir, D.
D, right? So diode D1 will be off and D2 is on. Very good response, Prakar and Ashwini. Keep going. Keep solving the problems. We know some concepts. Now we are applying our concepts. So make a habit of continuously sitting for 3 hours. We are doing class only for 2 hours, but cultivate the habit of sitting for 3 hours, because your gate exam is for 3 hours. You need to habituate to that. And remember, if you given plenty time, anybody can able to answer it. But the thing is, the rank deciding is in that on February 2nd week, during either morning session or afternoon session, whenever the exam is happening, during that time, in that 3 hours duration, you have to recall all the concepts which is there in the GATE syllabus. So for that, you need how much practice, right? So try to have a habit of sitting for continuously 3 hours, so that you don't feel difficult in GATE exam. So during that time, try to drink less water, but after 3 hours, try to relax more, so that slowly try to adapt to the 3 hours duration time slowly. Don't do it completely. How much is possible, that much you try to do, and slowly increase your time.
Yes, sir.
He's asking minimum and maximum values, but it's fine. With the given data, I'll try to solve. It is given that input is sinusoidal. Obviously, if sinusoidal is given, blindly go for during positive half cycle, during negative half cycle. What is the equivalent circuit and what is the output? It is asked to find out, obviously, uh, minimum maximum values of V naught, right? Output only it is asking. It is minimum maximum, I'll decide later, but I'll find the output during positive half cycle and negative half cycle. Obviously, during positive half cycle, diode will be fast bias, right? According equivalent circuit, and as cutting voltage is given, see, he try to understand this problem. I selected this problem. Cutting voltage is given, but it is saying ideal otherwise. Whether you need to replace with the short circuit or with 0.7. Which one you need to? Whether you need to replace with short circuit diode or with 0.7. Yeah? Any idea? Go
Short,
with the, yeah, Ashwini?
short circuit.
No short circuit. If it is given cut-in voltage in the problem, try to substitute, whatever it may be the case. And you have objectives, multiple choices are there here. Later we can compare with your result. If whatever data is given in the problem, try to use all the data. But sometimes in the problem they will give redundant information also. So that is also there. But for this dial problem, if cut-in voltage is given, use it. Don't replace with the short circuit, replace with the cut-in voltage only. So this is 2, cut-in voltage is 0.7. 1K, this is 1K. This peak value you consider. Peak value is 5, right? 5. So you want output, right? Output you want means you need drop across this 1 kilo ohm resistor. For that you need to find out current I. Find out current I. Till here you know, right? What is the voltage at that point? This is 2.7, right?
A negative half cycle, it will be
Yeah.
more
Going to negative half cycle. I don't know all those things. When I am in positive cycle, I'll think about positive half cycle only. Yes, Ashwini, you're saying something about negative half cycle. Anything else?
that will be reverse bias, right?
Obviously, reverse bias means open circuited, because we didn't given reverse bias means reverse resistance RR of the diode is not given. If it is not given, you assume it is ideal diode only. He clearly mentioned, right? Until otherwise ideal. Replace with at the time open circuit.
So, sir, if it's a reverse bias for a negative cycle, then the option can be from A and C only, no?
Option will be,
Option can be either A or C only, no?
yeah,
Like,
obviously,
yes.
either A or C. See, elimination concept you will get once you are solving so many problems. Okay, but in the beginning phase, try to go with the concepts. Then next level is minimum solving the problem, trying to identify the correct option. But this method, elimination method, won't help you much because these days equal weightage is there for MCQs and numerical answer type questions were there. So if all are MCQs, you can go with the elimination method. Whichever the problem is there, you keep on solving with the elimination method. But I think now it is not useful for you. Try to solve, but in the exam you decide. Or not only this, it is better recommended that you opt for any of the good institution test series. You may thinking that I'm doing good only, but you will understand after attempting their test series how where you are. So try to opt for. I think the money they are offering is some nominal only. I guess you can take it, but it is very important that you need to opt for a test series so that you have some goal always. They will put some deadlines, and this time this exam will be there, this exam will be there. But always try to stick to their timeline. You have your timeline because covering 8 subjects is not possible in these 3 months. So choose some subjects, focus on those subjects only, so that you can get some good marks in the GATE exam.
Yes, sir.
Always focus is yeah, Prakhar.
Nothing, sir. Nothing.
Focus is to solve the question asked in the GATE exam with less negative marking. So I will be 5 minus 2.7 divided by 2k, right? I will be here 5 is there. This resistance and this is open, right? So current won't flow there. This is open. Here V0 is there. Current won't flow, will go there. So whichever I is coming, it will enter here. So 5 minus 2.7 by 2k. How much is the current?
So 1.15 milliamps.
Yeah, 1.15 milliamps multiplied by 1k, right?
Yes, sir.
Obviously 1.15 volts across here. So 1.15 plus 2.7, right? 3.85. Obviously, so we got directly without seeing any light, take this answer, right? Whatever it may be that during negative half cycle. But during negative half cycle, this will be open. Once it is will be open, so there is no drop here. There is no current in this loop only, right? There is no drop here. Plus minus 5 like this, 5 volts. Same will be applied across output, but it is reversed. So during negative half cycle, output will be V not equal to minus 5. Fine. I think whatever is discussed till now is understood. I guess you can able to answer this. If you are confusing here, just sit right. The circuitry, simply twist it. But the thing is, input will be like this, output will be reverse. If you twisting, if you turn it, so above minus, below plus, this is output. So positive half cycle,
Sir, here only positive cycle will get rectified, I guess.
so what is the wave shape? Positive
Sine.
half cycle is output.
Yes, sir.
Output same shape will come.
No, sir, not not same. Clipped. Only positive cycle will get rectified.
What is the answer then? Here you have options A, B, C, D.
D, I guess.
Oi.
Or is it C?
C, sir.
Obviously, C. You see, equivalent circuit will be these two are short circuited, right? So V in will exactly appear at the V out, but different polarity. So that becomes like this. Output becomes like this. Why output will be 0 during positive half cycle? Na? See, positive half cycle is clearly mentioned from 0 to 0.5 t. From 0 to 0.5 t. How it will be 0? Like this. So during negative half cycle, both were reverse bias and open. Obviously, now we'll get 0. So C is the answer. Oh, without changing the circuitry, if you have any confusion like this, you can also solve. But ultimately, try to get the correct answer. Without changing circuit, I didn't change the circuit. This my change circuitry. So for this, while explaining one concept, see one bridge is there. Let us say this is R1, R2, R3, and R4. Anybody know bridge balancing condition? If I am saying this is balanced.
So R1 by R2 is equals to R3 by R4. So Wien bridge oscillator.
R1 by
R2.
fine. That also fine. This also fine. I remember like opposite resistance has to be multiplied. R1 multiplied by R3 equal to what? Opposite resistance has to be multiplied. R2 multiplied by R4. We are saying R1 by R2 equal to R3 by R4. Anything is fine, right? I remember like opposite resistance has to be multiplied. So now you multiply 6 into 2 equal to 4 into 3. Means if this is same, if this quantity is same, then bridge balanced. Bridge balance means the current here will be 0, right? So obviously the diode is totally eliminated only here, right? No current will flows. No current flows in this, right? The equivalent circuit becomes. Now, did you remember the current division rule? Current division rule. So this is 1 milliampere. This is 3, 6, 2, 4. What you want? You want current here, right? This is I1. If you want I1, what is the current division rule? 1 milliampere multiplied by opposite resistance, opposite arm. If I want in this arm, the current, if I want, I will take opposite arm resistance. Opposite arm resistance is 9 divided by total resistance. 9 plus 6 is 15. Is the current division rule. So you will get 9 divided by 15 is 0.6
0.6.
milliamperes. Right? So this is note, this is fill in the blanks question. Once you know only the based on one concept, if you don't know this formula, going with so many concepts, applying star, delta, all those things is so difficult, right? You don't know whether this is diode is forward biased or not because current source is given. One small concept, question got solved. If that concept is not recalled, gone. Yeah. Now this question, if you are able to solve, means today my effort was successful here. I am talking about average value, this, that, and all those mathematical definitions using in the something, right? If you are able to properly solve this and able to tell the average value, my effort is successful. And you are also learned something today. Means you learned or revised your concepts properly. You revised your concepts properly. Obviously, AC source I find means obviously positive half cycle, negative half cycle. During positive, what is the equivalent circuit? positive half cycle, plus minus like this, here plus, here also plus. So diode D1 will be forward bias and diode D2 will be reverse bias. So can you do simultaneously with me and tell me the answer? Let me see if you tell either me will tell the answer or you will tell the answer first. Assuming diodes D1, D2 are ideal clearly mentioned. That's why I'm going for short. Go according to given problem. This is open. Sorry. This is some 6 pi, right? Peak value is 6 pi only, right? So removing this, and I can draw this like this. Can I draw this like this? Because this is short only, right? Can I draw like this? This is 6 pi. Now again, this can be redrawn like this also, right? One resistor, two resistors like this. Connection here. Now voltage division rule, right? Voltage division. So this is 10K, 10K, 20K. You want at here, right? VAB. This is known already that 6 pi. Can you apply voltage division rule and tell me what is VAB? During positive half cycle? Did you got VAB? Voltage division rule. I want voltage here. 6 pi, that resistance. 10K only at this arc. Because anyhow, across this 10K, 6 pi is there. But across here, 10K followed by 20K, 6 pi is there.
So 2 pi.
Yeah, 2 pi sin omega t. Because
Yes.
this is AC, right?
Yes, sir.
30K. So that is VAB equal to 2 pi. Because it is asking average value. You need to know during positive half cycle what is the definition of VAB, mathematical definition of VAB, and negative half cycle also. That's why 2 pi sin omega t. And see, this is plus minus. So this is also measured also plus minus. So sign also same only will come. Now we will see during negative half cycle. Negative half cycle. Negative half cycle means here minus, here plus. So here also minus will be there. Now equivalent circuit will becomes, this will be open, right? Minus is there. Here D2 will be forward biased. This will be short circuited. According equivalent circuit will be, right? This is short circuit. So your voltage source will come here. Sorry, this is open circuit, right? Open circuit. This is short circuit. So your voltage source always will come here. From there till here, your voltage source will come. And then this will divide like this. This will divide like this. This is 6 pi, but polarities were minus plus. This is 20K, 10K, 10K. You want VAB here. Based on these polarities, you just see the current direction previously is like this, right? And now the current direction is reverse. Try to understand. VAB is here usually regarding the polarity. In this case also, current direction has to come like this one. Then I can say the same polarity as this I will get. But you see now the current direction is reverse. Previously across here current is entering. Now across here current is leaving. So based on that and applying the voltage division rule, 6 pi multiplied by 10K by 20K. So 3 pi I will get, but obviously sign will be different than previous because current directions were different. 3 pi sin omega t. Fine. Now you need to find out for that waveform average value. To find out average value. Here there are two ways are possible, but till now whatever I discussed, based on that only I am going. This is one way of current direction. You want one more way? Here, obviously, negative half cycle means the magnitude is minus 6 pi. This because that is one more method. I don't want to touch all those things. I will go with any one method. Fine. Average value. Can you apply integral and find out and tell me? So you need to apply positive half cycle 0 to pi 2 pi sin omega t dt plus integral pi to 2 pi minus 3 sin omega t 1 by 2 pi, right? 2 pi of and I this. I'm not writing completely. If you solve this, that only the basic definition, right? You know during first half cycle what is the waveform? What is the waveform in negative half cycle? Substitute in the formula. Any doubts in this? Solve and tell me how much you got the value. Anybody got the answer? Yeah. Did you got the answer? Yeah. Prakar? Nishal?
Sir, everything is coming zero now, sir. Like zero, sine zero is zero, sine pi is zero, pi and 2 pi
Sir, that's what.
become zero.
Minus 3 pi, na? Let me check because I already solved that.
Yes, sir.
Because that is minus 3 pi, na? Sin omega t integration is what? Minus cos omega t, na? Sin omega t integration. Minus cos omega t 0 to 2, 0 to pi.
Yes, sir. Minus cos omega t1.
There you will get plus 2, na? If you substitute the 0 to pi. Minus cos pi plus cos 0, na? Minus cos pi is minus of minus 1. There 2 you will get. And minus 3 keep it aside. And minus cos pi again pi to 2 pi. So minus 3 pi minus cos 2 pi plus cos pi, na? Again there you will get minus 2. Minus cos 2 pi is cos 360 plus 0. Means minus cos 0, right? Already minus is there outside. Minus cos 2 pi. This is already minus is there. Minus cos 2 it is, right? 360 plus. It is minus 1. Plus cos pi. Plus cos pi. Cos pi is minus 1. Cos pi is minus 1, right? So this is minus 1. Minus 1. Minus 2 will get. Here minus 3 pi is there already. That is plus you will get, na? So total
So you will get 5 pi, sir.
2 pi plus 3 pi. 5 pi. You will get no error. Wait. So here only you will get minus 2 pi. Already minus 3 pi is there here. Minus 3 pi is already there here. And minus 2. Minus 3 pi multiplied by minus 2. Plus 6 pi you will get. Only during pi to 2 pi. During this 2 pi you will bring it out. If this you do, you will get
That's
plus
4 pi, sir, totally. So
4
it will
pi.
be 10 pi and
Plus
then
4 pi.
1 by 2 pi thing.
And this is there, na?
5 pi.
So 10 pi by 2 pi. 5 pi cancels that. 5. So average value will be 5. So this only I'll try to realize. You just see here a blue line. Blue waveform is your given input, right? Blue waveform. What is the average value of that? Blue waveform. Now we discussed so many. Now I am trying to finally giving you the clarity. Try to answer this blue line only blue line. This is sinusoidal waveform, right? Positive is 6 pi, negative also 6 pi, minus 6 pi is there. Both are equal, right? You know sinusoidal waveform. What is the average value? Sinusoidal waveform.
0, sir. 0, sir.
0, na? Obviously, input you will have average value 0. But output if you see, positive is having the magnitude 2 pi. If you try to replicate, in the negative half cycle also, now negative half cycle, this is 2 pi, right? Minus 2 pi. Means this area will cancel each other, right? The remaining is, with the help of that integration, you are finding this area, this entire area, right? This area average value you are getting 5. Understood? Got the clarity? the small is there na? Between this is 2 pi, same waveform. This is 3 pi. This is 3 pi. This is 2 pi. This area is there, right? That area only giving you 5. You able to realize right now? Sinusoid will have 0, but how this I will get some positive value. I will get 0 only, na? You understood now, right? Why you won't get 0? You will get 5. 5 average value. Fine. If you have any doubt, please ask me. I'm closing the session today.